subset D of X is dense in X when the closure of D equal to whole of X. The closure of D equal to whole of X. Then we say that D is a dense subset of X. For example, rational numbers Q is dense in real numbers. In Euclidean topology, and it is very trivial because for any neighborhood of X, we have this example. The closure of Q equal to real numbers. Q is dense in real numbers because trivially the closure of Q is a subset of R. On the other hand, if X belong to R, X be a real numbers, then for each epsilon or we can write for each neighborhood of X such as U or N such as N we have there exists an epsilon such that this interval x minus epsilon, x plus epsilon is a subset of n. Now we know that this interval intersection by Q is non-empty set between any two real numbers. There is infinitely rational number. Okay, in this interval we have infinitely rational number. Section is non-empty because we know that non-empty. Because we know that this is a subset of n, and as a consequence we see that x minus epsilon, x plus epsilon intersect by n is a subset of, intersect by q is a subset of intersection of n and q. Since this is a non-empty set, this must be a non-empty set, okay? So that q is dense in R, real numbers. And also we have the definition of a base of a topology. Dear students, Mr. Abdul Rahman alias Shahmani, welcome. Do you have my voice? Okay. Mr. alias Shahmani, welcome. Welcome, thank you. And Salamun Alaikum Abdul Rahman. Okay. Let X and tau be a topological space. A subspace for tau is a set such as this. This is a subset of tau with the property that the set of all finite intersections of sets in F, for example, is a base. Let me write the definition of base as the first. Let X and tau be a topological space. A base such as beta for tau is a subset of tau where each open set in tau can be written as a union of elements in beta. Okay, can be written as a union of elements in beta, so that is a base for the topology tau, for example, if and only if for any u in tau there exists a family such as B alpha in beta such that u can be written as the union of this family. The union of this family. Any element of tau can be written as a union of a family of beta. Okay, there exists a family in beta such that u equal to the union of this family. A base such as beta. For tau is a subset of tau where each x and tau, a subbase for tau is a set such as F with the property that the set of all finite intersections of sets in F is a base for tau. Finite intersection, so that we must write for example F is a subbase for tau if and only if the following set is a base for tau. And this is considered sets, the set of all finite intersection. Okay, Fi from 1 up to the n such that n belong to n and F1 up to Fn belong to F. The set of all finite intersection of element in F. Finite intersection of element in F. Consists a base, be a base for tau. So that base and subbase are subsets of our topology. Example, let X and tau be a topological space where X equal to R to the power of 3 and tau is the Euclidean topology in this space. The set of all open box is a base. Open box. This is open box. For example, let me write example. Let X equal to R3 and tau equal to Euclidean topology. Euclidean topology defined in the previous session, we see that the union of all subsets of R, okay? The union of all open intervals in R. You can see the definition of Euclidean topology, and this is very, very important. Okay? Euclidean topology Then this is a base beta equal to the set of all open box such as this. AI, BI belong to R is a base for Euclidean topology and please note that the set of all open box. These are open box, okay? These are open box. And we know that for example, in this space, we can consider these open balls. Okay. This but not contain its boundary, okay? A1, B1, A2, B2, A3, B3. These are open intervals. Open intervals. The set of all these open cubes or open box is a base for Euclidean topology. The set of all open box is a base for this topology since any open is written as a union of open box. We know this. It is not that. This is the definition of Euclidean topology, okay? It is very important. The elements of Euclidean topology of Rn are of open balls in Rn, okay? So that any open set is a union of open box or open balls. Any open subset or in Euclidean topology is a union of open box, okay? And a subbase for tau is the set of all open box with volumes greater or equal 1. This is a subbase for tau since any open box can be written at a finite intersection of element in this subspace. The subspace given is not a base for tau because we would be unable to generate any open set of volume less than 1 since we can only take union. It's very trivial. And the following subset of tau is a subspace for Euclidean topology. F, for example, equal to the set of all elements in beta A1, B1, A2, B2, A3, B3 in beta such that its volume be great or equal 1. B1 minus A1 multiplied by B2 minus A2 multiplied by B3 minus A3 great or equal 1. Okay. This is a subspace because if we consider a family of all finite intersections of element in F, we reach to this beta, and we know that beta is the base, so that the set of all finite intersection element in F is a base, so that F is a subbase. F is a subbase. And also we have this definition. A fundamental system of neighborhood can be thought of as localizing the notion of a base around a single point. Let X and tau be a topological space, and let X belong to X, and let Ux be the set of all open neighborhoods of X. Let Vx be a subset of Ux. We say that Vx is a fundamental system of neighborhoods of X when for any Ux in Ux there exists some Vx in Vx capital with this property. Vx is a subset of Ux, and we say Vx is a base for ux. Fundamental system of neighborhoods. And we have this definition. A topological space X and tau is called a Hausdorff space when these things points can be separated by open sets, or equivalently for any x and y in X such that X non-equal y, there exist two open sets such as U and V such that X belongs to U, Y belongs to V, and the intersection of U and V the empty set. Okay, intersection of these two sets are empty set. Okay, let me write this again for you. We say that a topological space such as X and 2 is an Hausdorff space whenever let me instead of set X for example. Okay, its topological space is Hausdorff whenever for any two points such as X and Y. Okay, X and Y, there exist two open sets such as U and V, for example. U and V such that X belong to U, Y belong to V, and U and V be disjoint for any X and Y in X, there exists U and V in tau such that we have these three properties: X belonging to U, y belong to v, and u, the intersection of u and v equal to empty set. Then we say that x and 2 is Hausdorff. Hausdorff, okay? Example, Euclidean topology in R is Hausdorff. Euclidean topology. Let me write. Okay. As an example, Euclidean topology in R real numbers is Hausdorff, because for any, let me write this for you. For any x and y, in real numbers, we can consider two open sets such as this, two with these properties. For example, you can consider epsilon equal to y minus x divided by 3, okay? Then we can consider these two, x minus epsilon and x plus epsilon, y minus epsilon, y plus epsilon. These two open sets have these properties. Okay. Okay, you see this in this example, and we have the definition of continuous function. Let x and tau of x and y and tau of y be topological spaces, and let f from x to y be a function. We call f is continuous at x0 if the following holds: for any neighborhood of f of x0, the inverse image of f, the inverse image of n under f be a neighborhood of x0. And this is very nice definition. Okay. F from x to y is continuous at x0 if and only if the following holds for any neighborhood of f of x0, the inverse image of n under f is a neighborhood of x0. Okay, please note that please note that f from x and 2 of x to y and 2 of y is continuous at x0 if and only if or whenever if n belong to neighborhoods of f of x0, then the inverse image of n belong to the set of all neighborhoods of x0. And we know that for any if f from x to y is a function and a, for example, be a subset of y, then we know that the inverse image of a under f equal to the set of all x in x such that f of x belong to a. Okay, f of x belong to A. So that if we consider, for example, these two sets, x and y, and f be a subset from x to y, and we consider a subset of y, then we have this inverse image, for example, the inverse image of A under, okay, the set of all x such that f of x belong to A. F of x belong to A. The inverse image of A. Now, for the continuity at x0, for any neighborhood of f of x0, we know that this n is a subset of y. This inverse image must belong to the set of all neighborhoods of x0. Of x0. And we have this proposition. Let x and 2, y and 2y be topological spaces, and f from x to y be a function. The following three statements are equivalent. F from x to y is continuous on x. We say f is continuous on x whenever f is continuous in all points of x. Okay, we say that f from x to y is continuous on x if and only if f is continuous, f is continuous f is continuous at all points in x. Okay, now we have this proposition: f is continuous on x, or f is continuous at all points on x if and only if for any open subset of y the inverse image of u under f be open in x, and the inverse image of any closed set be closed set. All of these are equivalent. Okay, and the proof of this is easy, and we can see this. I sent for you this file. In this file you can see some examples and definitions. It is useful for you. Okay, Okay, this is very useful example for you. And I write some remarks and notes for you. All of this is very useful for you. The definition of a spot, and this proposition that a spot equal to this set. Okay, this is the definition of Hausdorff space. And finally, this proposition, the following statements are equivalent. F is continuous. For any open subset of Y, the inverse image of U must be open, and for any closed subset, the inverse image of F must be closed. I write the definition, the proof of this for you. For example, 1 implies 2. Let U be an open subset of Y. We must prove that this inverse image is an open subset of X. Okay? Then for each X in this set, we have F of X must belong to U. By this definition that I write for you, F of X must belong to U. Okay? But F is continuous at X. So, since U is a neighborhood, by our definition, the inverse image of U must be a neighborhood of X. Therefore, there exists an open subset of X such that X belongs to Ux and Ux is a subset of this neighborhood. For any X in this set, we have this Ux, so that the inverse image of U is equal to this union. For any X in this set, there exists an open set with this property. The union of this set equal to this, so that this is an open set. This is an open set. So that this is a neighborhood. 2 implies 1. Let 2 holds and X belong to X. We must prove that F is continuous at X. For this, let N belong to the set of all neighborhood of F of X. Then there exists an open set such as U by this property. No, by 2, this is an open subset of X. And since we have this inclusion, X belongs to this set, and this is a subset of the inverse image of N, so that the inverse image of N is a neighborhood. Okay, so this implies that F is continuous at X, and X is arbitrary, so that F is continuous in any point in X. And finally 2 implies 3. This is very easy, because if 2 be holds and F is closed subset of Y, then the complement of F is open. So by 2, the inverse image of this open set must be open, but the inverse image of this complement equal to the inverse image of y minus the inverse image of f. And this is equal to x. So that this is equal to the complement of this inverse image. The complement of this set is open. So that this set must be closed. And 3 implies 2, similar to 2 implies 3. So that these three conditions are equivalent. These three conditions are equivalent. Dear students, I sent this file for you. I write completely the proof of this statement for you. We can continue in the next session. Do you any question, dear students? Much and goodbye. Thank you very much. Goodbye for now.